In this video, we will discuss the fifth property of D block elements, that is variation in oxidation states. Variation of oxidation states. Now, one of the most important characteristic of transition element is that they can exhibit variable oxidation state. So, transition elements can exhibit variable oxidation state. Now, why they can exhibit variable oxidation state? Due to comparable energies of n-1d and ns orbital, maximum number of electrons are available for bonding. So, comparable energies means almost same energy of n-1d and ns orbital. Maximum number of electrons from n-1d and ns orbital can participate in bonding. So, transition elements can show variable oxidation state. Now, the most common oxidation state of transition element, common oxidation state is +2 except scandium. Scandium will not show +2 oxidation state. So, here comes a question, name a transition element which does not show any variable oxidation state, that is scandium. Scandium shows oxidation state equal to +3. +3 is the stable oxidation state for scandium, whereas all the other elements they show +2 oxidation state. Now, scandium can show +3 because you know the electronic configuration of scandium is argon 3d14s2. So, if it shows +3 means scandium 3+, the configuration will be argon 3d04s0, which means it has the noble gas configuration of argon which has scandium 3+, so it is highly stable. Now, so scandium does not show any variable oxidation state. The only oxidation state it takes is +3. Now, next we have the elements near the middle of each transition series exhibit maximum number of variable oxidation states. So, the elements in the middle of the series exhibits maximum variable oxidation state. For example, manganese. In the first transition series, in the middle we have the element manganese. Manganese can exhibit oxidation state. You know the configuration of manganese is argon 3d5,4s2. And manganese can exhibit the oxidation state +2, +3, +4, +5, +6, +7. Means the 7 electrons, all the 7 electrons, that is 5 electrons from 3d and 2 electrons from 4s can participate in bonding. So, it can show variable or maximum number of oxidation state, and this is it is manganese which shows the highest possible oxidation state, that is +7. Now, why that elements in the middle of the series can exhibit a maximum number of oxidation state? Because of the availability of maximum number of unpaired n-1d and ns electrons. Now, next we have transition elements showing zero oxidation state, especially in case of metal carbonyls. We have already seen this metal carbonyls example, NiCO 4 times. Then another example, FeCO 5 times. Now, the oxidation state of the metal nickel and iron in these compounds is equal to 0. Now, why they show zero oxidation state in metal carbonyls? Because the ligand, that is the CO group carbon monoxide ligand, it is capable of pi acceptor character in addition to sigma bonding also. So, the CO can have a pi bond character as well as sigma bond character. So, the central atom which are transition elements can show zero oxidation state. Okay. Now next there is an element in the first transition series which exhibit +1 oxidation state. So name the element of the first transition series which can exhibit +1 oxidation state. That element is copper. Copper, we know the electronic configuration is argon 3d10 4s1. Now after losing this one electron, what will happen? Cu becomes Cu plus with configuration argon 3d10. So it gets a stable electronic configuration 3d10 with no unpaired electrons. So this copper is the only element that exhibit +1 oxidation state in the first transition series. Now next we are going to compare the oxidation state of transition metals from non-transition elements. So we have the question, how is variability in oxidation state of transition metal differ from that of non-transition elements? Now the differences between the oxidation state of transition and non-transition elements are: transition elements show variable oxidation state. So I'll write in 2 columns. That is the difference, transition element and non-transition element. The difference in oxidation state. The first difference is transition elements can exhibit variable oxidation state. This is the first thing. Now why they show variable oxidation state? Because of the involvement of incompletely or unpaired N-1d and Ns electron for bond formation. But in case of non-transition elements, only Ns and Np electrons can participate in bond formation, so they cannot exhibit variable oxidation state. Now here no variable oxidation state. Now the next difference in the oxidation state is in non-transition elements, or we can say in p-block elements, the lower oxidation state is favorable for heavier members. Means we have down the group, the last elements are heavier elements, and lower oxidation state is favorable for heavier members, and we know the reason. That reason is due to inert pair effect. Okay, so for non-transition elements, lower oxidation state is favorable for heavier elements. Now for example, we know lead. Lead can show Pb2 plus and Pb4 plus, but Pb2 plus is more stable than Pb4 plus, because lead is the heavier element, last element of the group. Now when you compare the transition element, for transition elements the higher oxidation state is favorable for heavier elements. So for transition elements we can write higher oxidation state is stable for heavier elements. Now for example, we can say this is a chromium, molybdenum and tungsten. They are in the same group. Now we can say that chromium 6 is unstable, whereas molybdenum 6 and tungsten 6, they both are stable because they are the heavier elements, and chromium 6 is unstable. Okay, so this is the second difference. Now the third difference is oxidation state in transition elements differ from each other by unity, whereas non-transition elements differ by a unit of 2. So the third difference is oxidation state of transition elements differ by unity. We know that manganese can show +2, +3, +4. So the difference in oxidation state is 1. Whereas the non-transition elements, their oxidation state differ by unit of 2. Lead can exhibit 2 and 4, +2 and +4. So the difference is 2. So here they differ by a unit of 2. So these are the three differences between transition and non-transition elements with regard to their oxidation state. Okay. Now next we have a question. The question is Cr6 or dichromate. Dichromate means, example for dichromate is K2Cr2O7. This is potassium dichromate. Or we have another example, Na2Cr2O7. This is sodium dichromate. Now in dichromate ion, chromium has +6 oxidation states. Okay. This dichromate or chromium 6 in acid medium is a strong oxidizing agent. This is a strong oxidizing agent, whereas molybdenum trioxide and tungsten trioxide is not. Now the oxidation state of molybdenum in molybdenum trioxide is +6 and tungsten is also +6. So the question is, chromium 6 in acid medium is a strong oxidizing agent. Now we know that this chromium, molybdenum and tungsten, they all belong to same group. They belong to group 6 of the periodic table and they are all in +6 oxidation state. But we know that molybdenum 6 and tungsten 6, they being heavier members, their +6 oxidation state is stable than chromium 6. So what will chromium 6 do? It acts as an oxidizing agent so that it gets reduced to chromium 3+. So chromium 6+ gets reduced to chromium 3+, which is stable. So chromium 3+ is stable, whereas chromium 6+ is unstable. Okay, so that is this question. Now next we are going to see the oxidation states of oxides. Now for oxides, lower the oxidation state, then the oxide is basic in nature and it has ionic character. And higher the oxidation state, we have acidic oxide with covalent character. Now this is something very important, that is, if the you know that this transition elements, they can exhibit variable oxidation state, and in higher oxidation state they act as acidic oxide, and in lower oxidation state they will behave as basic oxide. And acidic oxides are covalent in nature and basic oxides are ionic in nature. Now example we have Mn2O3. Now let's find the oxidation state of manganese in this. Oxygen is -2, so manganese will be +3. So total will be +6 and -6 neutral molecule. Now Mn2O3 is ionic in nature, which means it has basic character. It's a basic oxide. Now another example is Mn2O7, where the oxidation number of manganese is +7, which is the highest possible oxidation state. In this case it will be covalent in character, which means it is an acidic oxide. Now this is an acidic oxide. Mn2O7 is an acidic oxide, so it dissolves in water to form an acid, and the acid produced is called permanganic acid. So oxides in lower oxidation states are basic and higher oxidation states are acidic in nature, and Mn2O7 dissolves in water to form an acid called permanganic acid with formula HMnO4. Now another example is we have chromium trioxide, CrO3. Now chromium oxidation state is +6, which is the highest oxidation state for chromium. This is acidic in nature. Acidic, and this chromium trioxide dissolves in water to form chromic acid. And the formula of chromic acid is H2Cr(O4), chromic acid. Now this oxides can also be in amphoteric state, means the intermediate oxidation states, they will be in amphoteric state also, and the amphoteric state oxide example is MnO2. MnO2, where manganese takes +4 oxidation state. This is an example for amphoteric oxide of manganese, that is intermediate oxidation state. So this you have to study one example for acidic oxide, basic oxide and amphoteric oxide of manganese. For basic oxide of manganese we have the example Mn2O3, acidic oxide we have Mn2O7 and amphoteric oxide MnO2 of manganese. Now next let us see a question, that is, we discussed that the lower the oxidation state, the oxide is basic in nature, and higher the oxidation state, the oxide is acidic in nature. Now the question is, the lowest oxide of transition metal is basic and the highest is acidic. Why? The answer is, in lowest oxide the metal will be in lower oxidation state. So it can lose more electron and behave as bases. We know that bases are electron pair donors. So lower oxidation state means it has low oxidation state, so it can lose more electron and behave as bases. But in higher oxidation state, metal will be in highest oxidation state. So the valence electrons will not be available for donation. So instead what they do, they will accept electrons and they behave as acids. So this is the reason why the lower oxidation state oxides behave as bases and higher oxidation state behave as acids. Now the next question is, this is the question. MnO is basic while Mn2O7 is acidic in nature. Now MnO is basic because in MnO the oxidation number of manganese is +2 and in Mn2O7 oxidation number of manganese is +7. We know that higher the oxidation number, it is acidic in nature, because in higher oxidation number they can not lose electron, they can only accept electron and act as acid. Now next we have the question, what is meant by disproportionation of an oxidation state? This we have already seen in the chapter redox reactions last year. So what is meant by disproportionation of an oxidation state, and give an example. So what are disproportionation reactions? Disproportionation reaction means transformation of a metal from a less stable oxidation state to a stable oxidation state, one lower and one higher. And an example is MnO4 2- plus 4H plus will give MnO4- plus MnO2 plus 2H2O. And when you write the balanced equation, 2 MnO4- and here we have 3 MnO4 2-. Now MnO4 2-, the name of this ion is, this is MnO4 2-, and this is MnO4-. Okay, and the name of this MnO4 2- is manganate ion. Now MnO4 minus is permanganate ion. KMnO4 is potassium permanganate, so the ion is permanganate ion. K2MnO4 is potassium manganate, so MnO4 2 minus is manganate ion. And you can see in MnO4 2 minus, the oxidation state of manganese is +6. Now +6 will get oxidized to +7 in MnO4 minus, and in MnO2 this manganese takes +4. So you can see +6 being an unstable oxidation state for manganese, it will change or disproportionate in acid medium H+ to higher and lower oxidation state. Higher oxidation state is MnO4 minus and lower oxidation state is MnO2. So this is a question. Explain disproportionation reaction with an example. Now next let us see the trends in stability of higher oxidation state. So next topic is trends in stability of higher oxidation states. Now again we have a question. The oxidation state of transition metal depends on the nature of combining atoms. Explain. Answer is, the compounds of transition metal with fluorine and oxygen exhibit higher oxidation state. Or this is also a question. The compounds of transition metal with fluorine and oxygen exhibit higher oxidation state. Why? You know that fluorine and oxygen, they have small size and they are the most electronegative element in the periodic table. So the answer is, due to smaller size and higher electronegativity of oxygen and fluorine, the compounds of transition metal with fluorine and oxygen exhibit the highest oxidation state. Now the next thing that we have to note is, fluorides are unstable in low oxidation state. So in low oxidation state, fluorides are unstable. For example, VF2, vanadium difluoride is unstable, means it does not exist. Whereas VCl2 or VBr2, these both exist. Okay. Now the next is, we said that we discussed that the compounds of transition metal with oxygen and fluorine, they exhibit higher oxidation state. Now the next thing that we have to notice, oxygen stabilizes the higher oxidation state of a transition metal more than fluorine. So when you compare oxygen and fluorine, who will stabilize the higher oxidation state of a transition metal? Oxygen. Now why? Why oxygen stabilizes higher oxidation state of transition metal more than fluorine? And the answer is, you know, both have small size and high electronegativity, but it is oxygen which stabilizes the higher oxidation state more. The answer is the ability, due to the ability of oxygen atom to form multiple bonds with central metal atom. For example, Mn2O7. Oxygen can form multiple bonds. When you draw the structure of Mn2O7, the structure is MnOMn. Then we have manganese forming double bond with oxygen. Okay, so the ability of oxygen to form multiple bonds with transition element, that helps oxygen to stabilize the higher oxidation state of transition element than fluorine. Now the next question is, the highest fluoride of manganese is MnF4. Highest fluoride of manganese is MnF4, but the highest oxide is Mn2O7. Why? You can see the oxidation state of manganese in this is +4 and Mn2O7 will be +7. And you know the oxides will stabilize, oxygen will stabilize the transition elements in higher oxidation state. Why? What is the answer for this? Because of the ability of oxygen to form multiple bonds. Now the next question. The next question is, how would you account for the increasing oxidizing power in the series VO2 plus less than Cr2O72 minus less than MnO4 minus? How will you account for the increasing oxidizing power? Means, first let's write the oxidation number of each element. In VO2 plus, vanadium is in plus 5, Cr2O72 minus, chromium is in plus 6, then in Mn, manganese is in plus 7. So we are increasing order is given, which means MnO4 minus is the strongest oxidizing agent. Why MnO4 minus acts as the strongest oxidizing agent? Because it wants to get reduced, and we know manganese is stable in plus 2 oxidation state. Same way Cr, chromium, it is stable in plus 3 oxidation state, and vanadium has the lowest oxidizing power. So the answer for this order is due to increasing stability of the species to which they get reduced. Okay, now the next question is, the highest oxidation state is exhibited in oxoanions of a metal. The highest oxidation state is exhibited in oxoanions of a metal. Now, oxoanion means they contain oxygen with a negative charge. That metal with oxygen carries a negative charge. Example, MnO4 minus, Cr2O72 minus, CrO42 minus, etc. These are examples for oxoanions, and you can see manganese has oxidation number plus 7 here, chromium has plus 6, the chromium here also plus 6. So the highest oxidation state is exhibited in oxoanions of a metal. Why? The answer is due to combination of oxygen, which is highly electronegative, and also oxygen can form multiple bond with the metal atom. Okay, now also this is an example. These ions MnO4 minus, Cr2O72 minus and CrO42 minus is an example of a oxometal cation showing highest oxidation state equal to group number. So the question can be asked, give example of a oxometal anion of manganese whose highest oxidation state is equal to its group number. We know that manganese is in group number 7. So, which is that oxoanion of manganese which has the oxidation state equal to group number? The answer is MnO4 minus. Now, again, if you are asked to name an oxide of chromium whose oxidation state is highest oxidation state is equal to its group number. Answer is Cr2O72 minus or CrO42 minus, and the chromium is in group number 6. Or if you are asked a question, name an oxometal anion of chromium whose highest oxidation number and group number are both same. In that case, you can write Cr2O72 minus or CrO42 minus. That is the answer. Okay. Now we have another question. Name an oxometal halide. Oxometal halide of vanadium showing highest oxidation state equal to group number. Now vanadium is in group number 5. So you have to write an example for a oxometal halide of vanadium. So the answer is VOX3. Now X is halogen. Let's find the oxidation state of vanadium in this. Now oxygen is minus 2. So this is minus 3 and minus 2. So vanadium will take plus 5, and group number and the highest oxidation state is +5 for vanadium, which are same. So this is the question. Name an oxometal halide of vanadium showing highest oxidation state equal to group number. Answer is VOX3. Okay. Now we have next question, that is cobalt 2 is stable in aqueous solution. But in presence of complexing agents, it is easily oxidized. We know that cobalt 2 is oxidized to cobalt 3. So in presence of complexing agents, it is easily oxidized, because in the presence of complexing agents, this cobalt 2 gets oxidized to cobalt 3, and cobalt 3 has greater tendency to form coordination compounds with the ligands. So in presence of ligands, this cobalt 2 gets oxidized to cobalt 3. Now the next question is the D1 configuration. D1 configuration is very unstable. In ions. Now, why the D1 configuration is unstable? Because the ions with D1 configuration, they have a tendency, only one electron is present in D orbital. So they have a tendency to lose that one electron present in D subshell to attain stable D0 or noble gas electronic configuration. So they are unstable and they undergo oxidation or disproportionation. Okay, so with this we completed the variation of oxidation states in transition elements. Thank you.